For our research project, we wanted to explore principles that were introduced in Lab 3 that examine distribution of elbow flexion and extension. Our research question was to investigate the impact that inertial changes have on arm movement when drawing simple figures. We later decided that sketching circles would allow for us to measure these effects. The variables used by prior research included elongation and the angle between the major axis of elongation and perpendicular to the forearm axis, which we call angle of orientation. Our method for collecting this data included two subjects that would sketch circles at a self-identified slow, medium, and fast speed. To test our hypothesis, we decided to have three arm orientation, which we call workspaces. These workspaces consisted of a constant upper arm axis angle of 60 degrees with respect to the torso and three elbow angles, 90, 115, and 140. 3 trials were conducted for each condition for a total 27 trials for each subject. After conducting experiments, we determined elongation ratio by measuring the circles by hand. These elongation measurements, along with conditions, were entering into an ANOVA test. Notice the F statistic is highest when associated with speed, second with individual, and last with workspace. This data conflicts with our hypothesis that arm extension affects elongation. Furthermore, we reviewed the data by condition with respect to elongation on box plots. Observe that the plots show no obvious trends with this workspace, but an interesting speed threshold may be implied when elongation increases. For our second hypothesis, we assumed that the angle of orientation would be close to the perpendicular axis with respect to the forearm. Thus, the angle measured would be 0. However, evidence from this study did not support this theory. From this data, we generated confidence intervals for the angle of orientation. In nearly all conditions for speed and workspace, these confidence intervals did not include 0 degrees. Thus, from the data, we are 95% confident that the true mean for each of these conditions is not 0. This result suggests that the forearm and elbow are not solely responsible for the inertial effects that influences sketching capacity. Our prediction is that since the resulting angle of orientation is closer to 0 degrees than 90 degrees, the forearm is dominant in control of the hand, but not the sole influencer. Before continuing, we would like to digress here for a moment to talk about our former method. Throughout the development and testing process, we encountered a number of issues that forced us to change the direction of data collection. Our original methods involved a pantograph device, secured to the subject's dominant hand with an elastic material. The pantograph was constructed from acrylic beams and Lego E3 motors, and was fixed to a table during data collection. The subject, attached to the pantograph and restricted to a single horizontal plane, would perform similar trials to those described in the methods section. During a trial, the encoders at the shoulder and elbow joint would measure their changing angles. They also would record the time between each data point, to account for delay in data collection. To analyze this data, we plan to convert the angle data into the global coordinate system, to track the Cartesian position of the hand as it drew the circle. However, when comparing these positions with the drawn circles, we discovered a lack of accuracy in the encoder data. The predicted hand coordinates did not match up with the actual path the drawing followed. We predicted this was due to the elbow and shoulder data being out of phase because of hardware issues, both with the pantograph and encoder abilities. We went through many iterations to attempt to mitigate this issue, including suspending the EV3 and adding extra support to the joints of the pantograph. However, we were unable to obtain viable data from this method of collection, and were forced to switch to a more analog technique. By switching to our current methods, we were able to focus on analyzing the degree and axis of elongation and their relationship to speed and workspace. In closing, this study, while limited, hints at the inertial effects of the arm on movement precision. Specifically the role that speed plays with respect to arm control and contributes to existing evidence that workspace does not. Our attempts at using a pantograph with Lego motor encoders showed these motors are not suited for this type of data collection. However, we were able to show proof of concept. Future researchers may be able to look at our technical difficulties and avoid this approach, but accomplish the aim of our former method. we were able to confirm that acrylic plates and Lego connections can build a suitable frame, but found that the motors fall short of accuracy and mechanical ability to record reliable data. Other studies mention the importance this work contributes to fields like neuropsychology, which demands more insight into the kinematic differences that can account for inertial forces operating at different arm and hand locations. Previous arguments have posed movements with hand trajectories perpendicular to the axis of the upper arm account for lower kinematic activity than more parallel hand trajectories. Our results contribute to this argument and corroborate that the angle of orientation was impacted by factors other than the forearm axis. Our study lays the groundwork for additional research, which can be conducted at low costs with an increased subject pool, to attempt to gather more information about how angle of orientation is influenced with the axis of the upper arm.